3.2 deals with maxima and minima. So again, we're talking about change of direction, which is going to relate to the sign of the derivative at certain critical points. A handful of notes, and I think how we want to take these notes is actually just use like the whole top of a page to sketch a function. And it doesn't really matter what your function looks like. I'm going to do a polynomial of degree 4, or at least it's going to look like that. Something like that. And I actually want this to be more obviously the minimum. Okay, so we have change of directions at 3 points. So we have a minimum here and a minimum here, and we have a maximum here. Okay, we're going to just name all of these points. So this guy over here is called a local, this is review, I'm sure, local minimum. What's true? Well, in its vicinity, in the values of x closest to it, it's the lowest value of the function. What does that mean? Well, it means from the left, you're decreasing to that point. You hit that point, and then you begin to increase. Okay? So what is true at a local minimum? A, f of a, the coordinates of that point, is a turning point. F of x changes from decreasing to increasing. How is that different from this guy over here? Well, this isn't a local min. This is an absolute min. Absolute min. It's similar to a local min in that from the left, the function is decreasing, and then it's a turning point to where it is increasing. But what's unique about this point is that the value of the function here is less than or equal to the value of the function for all values of x in the domain, essentially for the rest of the function. It's just saying that the value of the function here is less than or equal to the value of the function anywhere else along the function. Okay? Is less than the value of f of x for all x in the domain. But again, you can see how the derivative is going to have a change in sign from negative to positive. What about this guy up here? This is a local max, local maximum. Same thing is happening, just opposite. We are increasing to that point and then decreasing, which makes a f of a turning point. And I'm not going to write it, but you can say that the value of the function f of x, it changes from increasing to decreasing. And that is a local maximum. This function does not have a absolute maximum because you can see it goes its end behavior as x approaches negative infinity, f of x approaches positive infinity, and as x approaches positive infinity, f of x approaches positive infinity. So there is no absolute maximum. One other thing to note, I gave you a. So basically I represented the x coordinate as a, just an unknown value of x along the x-axis. Did that in every single case. What is that place called? That place where it changes direction? Any value of x where a change of direction happens, change of direction occurs, is called a critical value. Critical value. So what's true about a critical value? Maybe just in brackets. If it's a change of direction, then the value of the derivative at that point is 0. If it's a change of direction, then the slope of the tangent is 0. Yeah? You don't need to draw that dotted line if you don't need it, but it might be helpful for you to kind of see that the slope of the derivative at that point is 0, which means the value of the derivative function at that point is 0, or the other option is that the value of the function at that point does not exist. When would that happen? Well, if there was a gap or an asymptote or something like that. Okay, so if x equals a is a critical value, then f of a is a critical point. Okay, so all we're saying is that this point right here, the absolute min, is a critical point. The local min is a critical point, and this local max is a critical point. And in order to determine when and where that happens, the value of the derivative function will be 0 or won't exist at that point. So example 1. Example 1, you are given a picture of a graph. And we're going to consider it over the interval from 0 to 10. Identify the local maximum points. So go ahead and put a dot at the first local max. Call it A. There's another local max over here. And we're going to do local minimums as well. So just so we're all talking about the same thing, I've named them A, B, and C. There's also minimum points, a local minimum right here. So it looks like our function should keep going, but it doesn't. We're not considering those domain. So it satisfies the rule that within the domain surrounding it, it's a minimum point. We'll call that one D, A, B, C, D, and then we'll call this one E. So how do we know these are critical points? Well, the slope of the tangent at A will be 0. The slope of the tangent at B will be 0. The slope of the tangent at C will be 0. The slope of the tangent at D, well, the limit as we approach the point D from the right exists, but the limit approaching from the left doesn't exist. So this limit doesn't exist. The derivative doesn't exist, if that makes sense. Okay, what else do we need to talk about? Absolute max. There is an absolute max. It occurs at point C, which has a value of about 8. So in this case, the absolute max is 8 and occurs at the local max of C. And then the absolute minimum occurs at the lowest point on the graph. And at this case, the absolute minimum is here at 3. So if we want to make a little note, absolute min at 3, or of 3, I guess, would be better. It's the value of the function. And then you have an absolute max of 8. It occurs at x equals 8, and it is y equals 8. And the rest of these guys are local. Local max, local min, local min. Good enough. If you want to, you can draw the slope of your tangent lines there. And in example 2, we're going to use critical numbers. Use critical numbers. Remember, a critical number is anywhere that the graph changes directions. which means it's going to be where the derivative is equal to 0. So the function that we're given is f of x equals x cubed minus 12x minus 3.
Can a cubic have a maximum or absolute maximum or minimum?
Correct, it cannot have an absolute max or min.
It's awkward because you have a cubic here.
I'm maybe lying, so this example is actually telling us that it can have an absolute min and max, so I might have to eat my words on a lot of those notes that you just took. I don't know. Anyway, our step is to find the places where the derivative equals 0 because the derivative corresponds to the slope of the curve. So we first take the derivative, 3x squared minus 12. Then we set that equal to 0 and solve. 0 equals x squared minus 4. X squared equals 4. X equals plus or minus 2. Okay, so the local extrema, it's just another word for your local min or max, the extreme values, the local extrema that occur at x equal negative 2 and x equals 2. And then also the intervals. Oh, that's why we're going to have, because we're restricting the domain. So the domain of our function is negative 3. X is greater than or equal to negative 3 and less than or equal to positive 4. So that's why we end up with absolutes rather than just locals. Okay, so what are we going to do? We are going to find the value of the function at each of our extremas as well as the intervals, the beginning and end of our domain. Okay, so we can just put a list of what we're going to be finding out. We're going to find out the value of the function at negative 3. Again, I'm going to work left to right. We're going to find the value of the function at negative 2. We're going to find the value of the function at positive 2 and the value of the function at positive 4. So we found these critical points by using our derivative and the end bookends of our domain. And now we're going to sub them into the original curve to see what the value of the function actually is at that point, and that will allow us to identify the actual local max and min. So if I sub negative 3 in here, I get negative 3 cubed minus 12 times negative 3 minus 3. We can do that one. It's going to be negative 27 plus 36. Negative 27 plus 36 is going to be 11. Nope, 9. Minus 3 is going to get us 6. Okay, so the value of the function at x equals negative 3 is 6. Sub negative 2 in there, we get negative 2 cubed minus 12 times negative 2 minus 3. That gives us negative 8 plus 24. That's going to be 16. Minus 3 is 13. Sub 2 in there. I'm not going to write my sentence anymore. I'm just going to do it in my head. 2 cubed is 8. Minus 24 is going to get us negative 16. Minus 3 more is negative 19. And then sub 4 in there. 4 cubed is 64. Minus 48. Minus 3 more. It's going to get us 13. So then just taking this, we can identify our maximum value. The maximum value is positive 13, and it actually occurs twice. Max. Our minimum value is negative 19. It occurs once. Where do these things occur? Well, we can use that information to sketch our graph. It's kind of a tall, skinny one. So we have a max at negative 2, 13. So 1, 2, 3, negative 2, positive 13. We have a minimum at 2, negative 19, something down there. Then we have our max again at 4, 13. And at negative 3, we have a value of 6. So there-ish. So we're starting here. We're increasing to our first critical point. Our y-intercept, you can note here, is negative 3. 1, 2, 3. Call it there. Doesn't really matter. It's just a sketch. Coming down. Hitting our other local extrema. And increasing all the way to the end of our domain. And we don't know what the graph does beyond this point. Well, we kind of do. It just keeps going because it's cubic. And if you want to put some of the key points on here, we said our local max, our absolute max was going to be here at 13. This critical point is at 6. This was negative 3. Down here was negative 19. And where do they occur? They occur at negative 3, negative 2. I can just put in my... And you get a pretty good sketch. Again, critical points happen where the derivative function equals 0. You can find the value by subbing those critical points back into the original function. And here, since the domain was restricted, we had to figure out what was happening at the ends as well, because it turned out that we shared a local max here at 13. Example 3, maximum volume. So we have the surface area of a cylindrical container. We want it to be 100 centimeters squared. Example 3, cylindrical container. We want surface area to be 100 centimeters squared. Its volume is given by 50 minus pi r cubed, where r is the radius. There's r. In centimeters of the cylinder, we need to find the maximum volume of the cylinder in each case. So in A, the radius cannot exceed 3 centimeters. So r less than or equal to 3 centimeters. And in B, the radius cannot exceed 2 centimeters. So r less than or equal to 2 centimeters. And actually, we could put another boundary on this side. The radius needs to be greater than 0. Because if the radius were 0, the surface area and the volume would both be 0. Which doesn't make sense.
Do you have the function for the surface area?
We do not, and I don't think we need it. So let's look at each of these cases. In the first example, we have the radius cannot be less than 0, and it cannot be greater than 3. So we're going to find the critical numbers in this domain. So we got volume, which is here, 50 minus pi r cubed, and we're going to take the derivative of that, v prime. All we need to do is take our, so remember pi is just a number, it's just a constant, it's not a variable, so don't treat it like a variable. R is the only variable here, so all we need to do is take that 3 out front as the constant multiple rule, and then I guess the power rule, and then drop the derivative. So we're looking at 3 pi, oh, it's going to be negative, I believe. Oh, and I'm missing a letter. Ah, critical errors. This is 50r, the original function. I was wondering why that wasn't looking the same. So v is 50r minus pi r cubed. So our derivative is 50 minus 3 pi r squared. We want to set that equal to 0. We've got 3 pi r squared equals 50. We're going to divide both sides by 3 pi. We're not going to round at this point. And then we're going to take the square root of that. We could get a positive and a negative answer, but obviously the negative answer is going to be rejected because radius has to be positive. And click that in your calculator. You get a radius of approximately 2.3 centimeters. So over this domain, a radius of 2.3 centimeters will maximize the volume of the cylinder. Anyway, we would have to check the value of the function at all 3 points, so we'd have to sub in 0 because it's part of, it's a bookend of the domain, and we'd have to sub in 2.3 because that's the value that we found, and we'd have to sub in 3 because that bookends the domain, and I'm just going to write the answer for this one that we found because there's a change of direction there and nowhere else, so obviously that's going to be its max. It ends up being approximately 76.8, and volume is measured in centimeters cubed. The next domain is going to be slightly different because, I mean, you can see we're going to do the exact same situation, but the max that we reach isn't going to be included in the domain. So you would do the same amount of work, the critical numbers are going to be the same, but there are no critical numbers in this domain. We just found the critical number is 2.3, which isn't in the domain. So all we have to do then is check the value of the function at 0 and the value of the function at 2. The value of the function, I should be using v here instead of f, v, v. The value of the function, the volume when the radius is 0 is obviously 0. And the volume of the cylinder when the radius is 2 centimeters is approximately 74.9 centimeters cubed, which means that is the maximum volume in this domain. Because the critical value is not included in that domain. Okay, practice problems from 3.2 are found on page 163. You should be able to do 1 through 15.